Hello, my name is Min-Seo Jang. The title of my presentation is Stress Simulation of SISPAD inverters with some merged silicon germanium strain and wraparound contact. Semiconductor devices have advanced for decades by following Moore's law, which involves scaling down physical dimensions such as channel length and width. In particular, strained silicon technology was introduced at the 90 nanometer node to enhance carrier mobility. Stress is induced by performing silicon germanium substrate epitaxy or by depositing a high-stress film on the device. Since planar MOSFETs have a 100 surface orientation, hole mobility is inherently lower than electron mobility, making PMOS performance enhancement especially critical. In FinFET technology, the surface orientation is 110, resulting in hole and electron mobilities being relatively similar. However, with the introduction of nanosheet structures, the surface orientation reverts to 100, and strained silicon technology once again becomes crucial. Recently, SPAD technology has attracted significant interest as a way to reduce cell area by vertically stacking PMOS and NMOS devices. Our research group has developed an in-house process emulator to study state-of-the-art devices such as SPAD and SPAD. Using this emulator, we generated device structures and applied device simulation to analyze their electrical characteristics. However, we initially lacked a module to calculate stress. In this work, we integrated a stress simulation module into our in-house process emulator and investigate the stress behavior under process variations. This slide shows the methodology. Our process simulation is based on the Lebesgue method. By solving the Lebesgue equation, we track the evolution of surface and emulate process steps. For visualization, we use the closed matching cube algorithm. When simulating structure changes such as H or CMP, or depositing stress-inducing materials like silicon germanium, we need to calculate stress. Based on the extracted boundaries, we generate a tetrahedral volume mesh using the Jang library. We then solve the equation of equilibrium to compute stress. The equation states that the sum of all internal and external forces acting on every point in the structure must be balanced. Using the stress-strain relationship and the strain-displacement relationship, we discretize the equation of equilibrium using the finite element methods to calculate stress. This slide shows the process simulation and stress simulation results for a SISPAD inverter with varied power layer. In the bottom tier PMOS, silicon germanium substrate is used to apply compressive stress. In the top tier, there is no silicon bulk, so the same approach cannot be used. Instead, silicon substrate is used. The graph on the right hand shows the channel direction stress current for PMOS and NMOS. In the silicon germanium stack structure, only the silicon germanium layer experiences compressive stress due to lattice mismatch. During pin patterning and source drain edge, the silicon germanium layer relaxes, which induces tensile stress in the silicon layer. PMOS channel receives compressive stress from the silicon germanium source drain epitaxy, while the NMOS silicon source drain does not induce stress. The channel release process causes a negative stress shift for both PMOS and NMOS. Finally, the peak channel stress is calculated to be minus 1.9 gigapascal for PMOS and 0.3 gigapascal for NMOS. During source drain epitaxy, multiple growths can cause defects. In our simulation, defect regions were modeled as void. Horizontal defects results in a 19% stress reduction, and vertical defects cause a sign change in stress. Since electrons benefit from tensile stress, vertical defect can be advantageous for NMOS strain. When considering inverter operation alone, it is preferable for PMOS and NMOS to have balanced drive strength. However, in applications such as SRAM, having a stronger pull-down strength is advantageous. To use this, we designed an NMOS structure where the source drain is not merged with that of neighboring device. This naturally forms a wraparound contact, reducing contact resistance. For the bottom tier, we also used wraparound contact, but surrounded one side of the source with dielectric material to maintain spacing between metal lines. Here are the stress calculation results for this structure. First, for NMOS, we confirmed that using unmerged silicon germanium substrate induced tensile stress in the channel. When a horizontal defect is present, the stress is reduced, and this matches the results we saw earlier for PMOS substrate with horizontal defect. On the right-hand side, you can see the results when a wraparound contact is applied to PMOS. In this structure, the drain side is completely surrounded by metal, whereas on the source side, only half of it is wrapped with metal. Because of this difference, the stress distribution becomes asymmetric as shown in the graph. Since the metal modulus is larger than that of the low-K dielectric, the stress change during the channel release process becomes smaller. As a result, compared with the conventional contact structure, we observe about a 19% reduction in stress. In this study, we integrated a stress simulation module into our existing in-house process emulator. Using this tool, we performed process emulation and stress simulation for a SISPAD inverter with BPR and analyzed the impact of source drain defects and wraparound contacts on stress. For future work, we plan to induce a mobility model that accounts for stress effects in our in-house device simulator so that we can perform full device level simulations that capture stress-induced performance changes. In addition, we will perform KLMC simulations to predict the shape of source drain epitaxy growth, which will allow us to improve the accuracy of our process emulation even further. This is my poster. Thank you for watching this video.